Imagine stepping into a world where the biggest threats aren't, colossal monsters or towering infernos, but rather microscopic, single-celled organisms invisible to the naked eye.
Mm-hmm.
These tiny entities possess an astonishing capacity to wreak havoc across continents, causing debilitating diseases that quietly yet profoundly affect millions of lives.
It's quite staggering when you think about it.
We're not talking about some far-flung science fiction scenario.
Yeah.
This is a very real and persistent challenge unfolding right now, reminding us that some of the most surprising and enduring threats to global health are, in fact, incredibly small.
Okay, let's unpack this. Today, we're taking a deep dive into the fascinating and sometimes alarming world of protozoal infections.
Right.
These are single-celled organisms distinct from bacteria or viruses that can cause a surprising range of diseases across the globe, and they present some truly unique challenges for diagnosis, treatment, and especially for global eradication efforts. Exactly. Our sources for this deep dive give us a comprehensive and intricate look at not just how these infections spread, but the specific diseases they cause, and critically, the sophisticated ways medicine has learned to combat them. What's truly compelling here is understanding not just the nature of the diseases themselves, but the intricate strategies and ingenious chemical pathways behind the drugs designed to fight them, often targeting vulnerable points in the parasite's complex life cycles.
Our mission for you today is to leave this deep dive exceptionally well informed about these often overlooked health threats, understanding their profound impact on human populations, and appreciating the intricate, often heroic science behind the antiprotozoal agents developed to protect us. Get ready for some genuine aha moments about a microscopic world that has disproportionately large implications for human health and global development.
Definitely some aha moments in here.
So let's begin at the most fundamental level. What are protozoal infections? When we use this term, we're referring to diseases caused by protozoa, which are eukaryotic single-celled organisms.
Right, eukaryotes. More complex than bacteria.
And unlike bacteria or viruses, these organisms are far more complex, with internal structures and life cycles that make them incredibly adaptable and often harder to eliminate. But what truly sets them apart and what makes this deep dive so interesting is their incredibly diverse methods of transmission. It's certainly not just one way these little guys get around, which means our defensive strategies have to be equally varied.
That's a crucial distinction. When you examine the primary pathways of infection for protozoa, you can really categorize them into two major groups, each associated with its own set of globally significant diseases. The first, and arguably most widely recognized, are those transmitted through insect bites.
The vectors, like mosquitoes.
Exactly. This isn't just a simple route. It's a critical pathway that highlights the incredibly intricate, often delicate, dance between these pathogens, their specific insect vectors, and the human populations they affect. Consider malaria, for instance. It's the quintessential example here, notorious for its devastating global significance, primarily transmitted by specific species of Anopheles mosquitoes.
The scale of malaria is just enormous.
Staggering. The sheer scale of its impact on human health, especially in tropical and subtropical regions, is staggering, claiming hundreds of thousands of lives annually and causing debilitating illness in millions more. But the story doesn't end with malaria. We also have trypanosomiasis, which encompasses diseases like African sleeping sickness, transmitted by the tsetse fly.
Right, sleeping sickness.
And Chagas disease in the Americas, carried by the kissing bug. Both are debilitating chronic conditions if left untreated. And then there's leishmaniasis, a complex array of diseases caused by parasites transmitted by the bite of infected sandflies, leading to a variety of clinical manifestations from disfiguring skin sores to severe, often fatal, internal organ damage.
Wow. Quite a range just from insect bites.
It is. And what's truly insightful here is how this highlights the pervasive, undeniable role of environmental factors and specific insect vectors in disease transmission. This is a connection that's often overlooked when we're just thinking about getting sick from a virus or bacteria. It's not merely about person-to-person spread, it's about the entire ecosystem, the climate, the geography, the insect populations, and their interaction with human habitats.
That's a vital distinction. It really paints a clearer picture of how our environment and even tiny insect populations can be direct conduits for disease, blurring the lines of how we typically think about infection.
So when we talk about this environmental connection, what are the explicit risk factors that amplify this spread? And you mentioned a second category of transmission, distinct from insect bites. What does that look like, and how do those factors play in?
Right, the second major pathway. This involves ingestion or direct contact with the causal organism.
So contaminated food or water, things like that.
Exactly. This category often points directly to widespread issues with sanitation and hygiene, as these organisms are frequently found in contaminated food, water, or spread through direct human-to-human transmission. Think of amoebiasis, for example. It's typically acquired through the fecal-oral route, meaning the parasite is ingested when people consume food or water contaminated with microscopic cysts.
Yeah. This leads to severe intestinal illness or dysentery, and in some cases, the parasite can even invade other organs like the liver, forming dangerous abscesses. Similarly, giardiasis is very commonly associated with contaminated water, often what people colloquially refer to as beaver fever.
Ah, I've heard of that one. From camping trips, maybe?
Could be from drinking untreated water in the wilderness or from inadequate water treatment in urban areas. It causes prolonged, severe gastrointestinal upset. And then there's trichomoniasis, which is a sexually transmitted protozoal infection caused by Trichomonas vaginalis.
So direct contact, but a different kind.
Precisely. This highlights an entirely different mode of direct contact, distinct from environmental contamination. It's a very common STI that, while often asymptomatic, can cause discomfort and increase the risk of other STIs and even pregnancy complications. The illustrative content here really underscores the distinct nature of these transmission routes. Understanding whether an infection is insect-borne, waterborne, foodborne, or sexually transmitted is absolutely fundamental.
Because it tells you how to stop it.
Exactly. It directly informs our public health interventions and prevention strategies. You can't fight all protozoal infections with the same set of tools. You have to consider how they spread and, more broadly, the environmental conditions that facilitate that spread.
So we've identified these two major transmission routes, insect bites on one hand and then ingestion or direct contact on the other. But it seems to me, especially with those ingestion-related infections, there's a deeper story here about our environment and even our societal structures playing a role. How explicit do our sources get about these broader risk factors that connect these microscopic threats to wider public health challenges?
Oh, very explicit. Precisely. The sources detail a couple of critical systemic risk factors that dramatically amplify the spread of these organisms, particularly those acquired through ingestion or direct contact. The first is unsanitary, crowded conditions.
Yeah.
Imagine densely populated urban slums, areas hit by natural disasters, or large refugee camps where basic infrastructure for waste disposal and access to clean water are either overwhelmed, non-existent, or severely compromised. In these environments, protozoa can thrive and spread rapidly through communities simply due to the lack of proper waste management and safe water sources. It creates a perfect storm for outbreaks.
A breeding ground, essentially.
Exactly. And hand in hand with that are poor hygienic practices. If people don't have consistent access to clean water for washing, or if they lack awareness or education about proper hand hygiene, safe food preparation, or safe sexual practices, the risk of exposure and subsequent infection dramatically increases.
Right. Basic hygiene becomes a major barrier.
A huge barrier. And this connects directly to public health implications on a massive global scale. If we connect this to the bigger picture, it profoundly underscores how deeply global health disparities are intertwined with basic infrastructure, socioeconomic conditions, and access to fundamental resources. It's not just about providing medical treatment after someone gets sick, it's about preventing illness by addressing the fundamental living conditions that allow these parasites to flourish.
So public health is preventative infrastructure as much as medicine.
Absolutely. The aha moment here, often overlooked, is realizing that fighting these diseases isn't solely about pharmaceutical development. It's fundamentally about environmental stewardship, urban planning, and accessible public health education. Think about it. A seemingly distant factor like climate change, by altering mosquito habitats, directly fuels malaria outbreaks in new regions.
Wow.
Or crumbling public sanitation in a bustling city can unleash a wave of waterborne protozoal illnesses. Our global health isn't just in our hospitals. It's deeply connected to the health of our planet and the robustness of our societal infrastructure.
It makes perfect sense and truly elevates the conversation beyond just the biology of the parasite. Improving access to clean water, building proper sanitation facilities, and investing in widespread health education are arguably some of the most powerful, often overlooked tools in combating a significant portion of these protozoal infections, even before we get to the specific drugs.
Couldn't agree more. Foundational stuff.
Speaking of which, let's pivot to what is arguably the most well-known protozoal infection globally, malaria.
Ah, yes, malaria.
It's a relentless challenge that has plagued humanity for millennia, and despite significant global efforts and enormous resources poured into its control, it remains a persistent and deadly threat. What makes it such a significant ongoing challenge in the 21st century?
Malaria's impact is indeed immense, and a core reason for its continued severity lies in the specific Plasmodium parasites that cause it. Our sources highlight critical distinctions among these species, which are absolutely crucial for understanding both the widely varying disease outcomes and the targeted treatment strategies required.
Okay, so it's not just one malaria bug.
No, definitely not. First and foremost, we have Plasmodium falciparum. This species is explicitly stated as the most dangerous type of protozoan causing malaria.
The most dangerous. Why?
This distinction is paramount because P. falciparum is responsible for the vast majority of malaria-related deaths globally. It can rapidly lead to severe, life-threatening complications like cerebral malaria.
Affecting the brain.
Yes, where the parasites affect the brain, leading to coma and neurological damage, severe anemia due to massive red blood cell destruction, or multi-organ failure if not diagnosed and treated promptly and effectively. It progresses quickly and aggressively.
That sounds terrifyingly fast.
It can be. Then, in stark contrast, Plasmodium vivax is described as a milder form of the disease that seldom results in death.
Milder, but still bad, I assume.
Oh, definitely. While it can still cause debilitating illness with cyclical fevers and chills, its acute presentation is generally less severe than P. falciparum. However, P. vivax has a unique trick. It can form dormant liver stages called hypnozoates.
Hypnozoates, like sleeping forms.
Exactly. They can lie low for months or even years, causing relapses long after the initial infection is cleared. This means that while the acute disease is milder, sustained treatment is needed to prevent recurrence.
Sneaky, so it comes back later.
It can. Then there's Plasmodium malariae, which is endemic in tropical countries. What's particularly interesting and important about this species is the noticeable difference in symptoms between local populations and travelers.
How so?
In local populations and endemic areas, it often causes relatively mild symptoms, perhaps due to some level of acquired immunity or continuous exposure over time.
Okay.
However, for travelers to these endemic areas who lack that immunity, it can present as a more acute, significant disease, leading to substantial illness because their immune systems are encountering it for the very first time.
So travelers beware. That's a crucial nugget, as you said.
Absolutely crucial for anyone considering travel to malaria-prone regions. Finally, we have Plasmodium ovale. Our sources indicate it's caused by two different species, P. ovale curtisi and P. ovale wallacuri, and both are most prevalent in Africa.
Okay, another one mainly in Africa.
Yes. And what's truly concerning about P. ovale, and a detail that introduces a significant growing challenge for eradication and control efforts, is the explicit mention that the mosquito has developed resistance to insecticides in relation to this species.
Resistance, that's bad news.
It's very bad news. This isn't just a minor technicality. It strikes at the very heart of current public health strategies. If the primary vector, the mosquito, becomes resistant to the insecticides used in bed nets and indoor residual spraying,
Which are cornerstone prevention tools.
exactly, then the entire strategy for preventing transmission is undermined, allowing the parasite to continue its spread unimpeded. What's truly fascinating here, if we think about it, is how these subtle biological differences in parasite species can lead to vastly different disease outcomes and even critically complicate global control efforts, especially when we face developing insecticide resistance.
It's an arms race.
It really is an ongoing high-stakes arms race between human ingenuity and parasitic evolution, constantly demanding new solutions.
That developing insecticide resistance for Plasmodium ovale is genuinely alarming. It makes you realize this isn't a static battle. The parasites, and even their vectors, are constantly evolving, demanding we evolve our strategies too.
Precisely. We can't stand still.
So once these adaptable invaders do take hold, what exactly happens inside the human body? What are the immediate effects that tell us malaria has taken hold, and how do those effects directly inform the strategy for treatment?
Okay, so when malaria parasites, primarily Plasmodium, invade the human body, the classic signs and symptoms you see are directly related to two major destructive processes: the cyclical destruction of red blood cells and significant toxicity to the liver.
Red blood cells and the liver, got it.
This explains why patients experience the incredibly debilitating symptoms: the signature cyclical fever and chills, which can feel like an alternating oven and ice bath,
Sounds awful.
occur as parasites mature and then burst out of infected red blood cells, releasing toxins and parasitic waste into the bloodstream. This massive, synchronized destruction of red blood cells also leads to profound anemia, causing extreme fatigue, weakness, dizziness, and paleness.
Anemia makes sense if red cells are being destroyed.
Right. Simultaneously, the liver is a primary site where the parasites multiply in their initial stages after being injected by the mosquito. Their rapid multiplication and metabolic activities within liver cells can cause significant hepatic dysfunction, contributing to the overall systemic illness.
So the liver gets hit early on.
Yes. And understanding this destructive mechanism is absolutely foundational to designing an effective treatment strategy. The core principle of malaria treatment, as detailed in our sources, aims at attacking the parasite at the various stages of its incredibly complex development, both inside and outside the human body.
Multiple stages need multiple attack points.
Exactly. If you consider the intricate life cycle of Plasmodium, which, while we don't delve into every microscopic detail, involves distinct phases in the mosquito, then the human liver, then the human red blood cells, and finally back to the mosquito, it truly reinforces the complexity of the parasite's journey within the host. Because the parasite has these multiple distinct phases where it undergoes different transformations, a successful treatment strategy can't just hit one target or one stage.
It needs to be comprehensive.
It needs to be comprehensive, often involving a combination of drugs that target multiple stages simultaneously to effectively clear the infection, prevent its recurrence, and even prevent its further transmission to mosquitoes. This multi-pronged complexity justifies the sophisticated multi-stage attack strategy we see employed with modern antimalarial drugs.
Given that intricate life cycle, it almost seems intuitive that you'd need a multi-pronged attack, hitting the parasite at different stages. Is that precisely how this antimalarial arsenal is designed to work?
It is.
And what does that antimalarial arsenal actually look like? What are the specific drugs that have been developed to combat malaria?
It's precisely how it's designed to work, and the arsenal is quite diverse, including some historically significant agents alongside crucial newer developments. Perhaps the most iconic is quinine, also known by its brand name Qualiquin.
Quinine. From tonic water, right? Well, historically.
Ah, yes, historically linked. This was literally the first drug discovered to be effective in treating malaria, dating back centuries to its extraction from the bark of the cinchona tree. What's truly remarkable is its history. It actually vanished from the market for a while, almost like a forgotten relic of medicine, but it has now made a significant, almost heroic comeback and is available again for treating uncomplicated malaria.
Wow, a comeback story for a drug.
It really is a compelling what's old is new again story, demonstrating that sometimes the most enduring solutions are found, revisited, and reimagined, especially as drug resistance patterns evolve.
Fascinating. What else is in the arsenal?
Beyond quinine, the key drugs used for malaria treatment include chloroquine, widely known by its brand name Aralen.
Chloroquine, I've heard of that.
Yes, it was once the most commonly used antimalarial, but now faces widespread resistance in many regions.
Resistance again.
Yeah, it's a recurring theme. Then there's hydroxychloroquine sulfate, or Plaquenil, which has gained broader public awareness recently for other uses, but remains an important antimalarial. We also have mefloquine, available generically, which is often used for malaria prevention in travelers to high-risk areas due to its long half-life.
The traveler's friend, perhaps.
Sometimes, though, it has its own considerations. Primaquine, also generic, is uniquely effective against the dormant liver stages of P. vivax and P. ovale, preventing relapses.
Targeting those sneaky hypnozoids.
Exactly. And then some crucial newer agents like tefenaquine, which goes by Aracoda or Crintafel, also effective against those dormant liver stages and for prevention.
So newer options are still appearing.
Absolutely. For each of these, their general use is centered on the treatment and prevention of malaria, often selected based on the specific Plasmodium species involved, the geographic region, due to crucial drug resistance patterns, and the patient's individual circumstances.
Like age, pregnancy.
Exactly. Age, pregnancy status, coexisting health conditions. It's truly incredible to see how a disease like malaria requires such a diverse array of drugs, each with its own history, mechanism, and specific role in this ongoing, complex fight.
It really is a testament to centuries of scientific effort and persistent research. So we know what these drugs are, but how do they actually wage war on these microscopic invaders at a cellular level? And given their power, what are the crucial safety considerations? Is there a common thread in how they work, or are they all completely unique in their approach?
That's an excellent question, and understanding how antimalarials work is key to appreciating their effectiveness and also their limitations. Our sources describe their actions using various incidental terms.
Meaning killing.
Exactly. They relate to the specific stages of the parasite they target within the human body and the mosquito. For example, schizonticidal means the drug kills schizonts.
Which are the ones in the red blood cells?
Correct. The forms of the parasite that multiply rapidly inside red blood cells. This action is absolutely crucial for stopping the acute, debilitating symptoms of malaria, as the bursting of these infected red blood cells causes the cyclical fevers, chills, and anemia we discussed. Then there's gametocytocidal, meaning the drug targets gametocytes.
Okay, what are those?
These are the sexual forms of the parasite that are picked up by mosquitoes from an infected human. So, by killing them, the drug helps prevent further transmission of the disease from humans to mosquitoes, breaking the cycle.
Topping the spread. Smart.
And sporonticidal agents target the sporonts, which are forms of the parasite that develop within the mosquito itself, again aiming to break the transmission cycle at its source. Beyond these direct killing actions, some antimalarials also work against tissue schizonts as prophylactic or anti-relapse agents.
So, prevention and stopping those relapses from Vivax and Ovel.
Exactly. This means they can be used for prevention, prophylaxis, preventing the initial infection from taking hold in the liver or bloodstream, or to prevent relapses. In terms of pharmacokinetics, which is the fascinating study of how the body processes these medicines.
How the body handles the drug.
Right. It varies by drugs. This isn't just a throwaway line, it's absolutely critical. Imagine some drugs are like sprinters, quickly absorbed and processed, while others are like marathon runners, lingering in the system for longer.
Which affects dosing and side effects.
Absolutely.
Yeah.
This dictates everything from how often you take a pill to potential drug interactions and side effects. For a clinician, understanding these unique journeys for each medicine is absolutely fundamental to safe and effective dosing, ensuring the drug reaches the parasite at the right concentration for the right amount of time.
Okay, so understanding how they work is key. What about the safety side? The contraindications and cautions?
Critically important. Now, regarding crucial considerations for patient safety, contraindications and cautions are paramount, requiring careful attention from prescribers. These are not minor warnings. Overlooking them could lead to severe health consequences. For instance, a known allergy to the drug is an absolute contraindication, giving it would trigger a potentially life-threatening allergic reaction.
Obvious, but essential.
Essential. Liver disease and alcoholism are significant concerns because many of these drugs are extensively metabolized in the liver, and impairment can lead to dangerous drug accumulation and increased toxicity, potentially exacerbating liver damage.
So you need a healthy liver to process them safely.
Often, yes. Pregnancy and lactation are critical considerations due to potential harm to the developing fetus or infant, requiring a very careful risk-benefit analysis by the clinician.
Always tricky in pregnancy.
Always. Conditions like retinal disease or damage are listed because some antimalarials, notably chloroquine and hydroxychloroquine, can cause irreversible retinal toxicity.
Irreversible. Wow.
Yes, leading to permanent vision loss if not carefully monitored. Psoriasis, a chronic skin condition, and porphyria, a rare group of genetic disorders that can affect the nervous system or skin, are also specific contraindications, as some antimalarials can unfortunately exacerbate these underlying conditions, leading to severe flare-ups or neurological crises.
Okay, quite a list of things to watch out for. What about side effects, the adverse effects?
Yes, as for adverse effects, antimalarials can have a broad range, impacting multiple body systems. We commonly see effects on the central nervous system, CNS.
Like what? Headaches?
Headaches, dizziness, sleep disturbances, and in more severe cases with certain drugs like mefloquine, even anxiety, depression, seizures, or psychosis.
That sounds serious.
It can be. Immune reactions, including various types of rashes and hypersensitivity reactions, are possible. Gastrointestinal, GI issues like nausea, vomiting, abdominal pain, and diarrhea are quite common.
The usual suspects for drug side effects.
Often, yes. Hepatic dysfunction or liver problems can occur, manifesting as elevated liver enzymes or rarely more severe damage. Various dermatological effects like skin rashes, itching, or pigmentation changes can also be observed. Vision changes, beyond the serious retinal damage we mentioned, such as blurred vision or difficulty with accommodation, can also be temporary side effects. And a very specific, memorable adverse effect, particularly associated with quinine toxicity, is synchonism.
Synchonism, what's that?
This is a distinct constellation of symptoms, including ringing in the ears, tinnitus, headache, nausea, disturbed or blurred vision, dizziness, and sometimes diarrhea. It's a classic example of drug-induced adverse effects that serves as a specific warning sign for clinicians.
Ringing ears, headache, vision issues. It's good to know that specific pattern.
Very. Finally, drug interactions are a major concern, given that patients often take multiple medications.
Right. People rarely take just one thing.
Exactly. For example, a patient who is receiving combinations of a quinine derivative, like chloroquine, and quinine itself is at increased risk for cardiac toxicity and convulsions.
So combining similar drugs can be dangerous.
Very dangerous. This is a particularly serious warning because combining similar drugs can lead to amplified, dangerous side effects on the heart's rhythm and brain activity, interactions with antifolate drugs, which are medicines that interfere with how cells use folic acid.
Folic acid important for blood cells.
Yes, a vitamin vital for cell growth and especially for the production of red and white blood cells. These interactions can also be problematic, potentially leading to issues like severe anemia or immune suppression due to their combined effect on blood cell formation. And crucially, if a patient is on hydroxychloroquine and also taking drugs that lower the seizure threshold, certain antidepressants or antipsychotics, for instance, their risk of seizures can dramatically increase.
Wow.
Making careful medication reconciliation and patient history absolutely essential before prescribing.
This truly brings into sharp focus just how complex medication management becomes when treating such a multifaceted infection, especially considering all these potential interactions and adverse effects. It's not just about prescribing a pill, it's a careful, intricate balancing act for clinicians, isn't it?
It's incredibly complex, requiring profound clinical judgment. Clinicians have to meticulously weigh the specific Plasmodium species identified, local drug resistance patterns, the patient's coexisting medical conditions, all other medications they're currently taking, and their unique risk profile based on age, pregnancy status, and genetic factors.
A lot to juggle.
A huge amount. It truly demands a deep understanding of pharmacology, pathology, and patient-specific factors to ensure maximum efficacy while minimizing potential harm. It's a precision science.
We've spent a good amount of time on malaria, and rightly so, given its global impact and the sheer complexity of its treatment. But malaria, while profoundly significant, is just one piece of the protozoal puzzle.
Absolutely. Just one, albeit a big one.
Our sources highlight a spectrum of other important protozoal infections. What are they? And why are they also important for us to understand in this broader context of global health?
That's a vital point. Beyond malaria, our sources list several other significant protozoal infections, underscoring the incredible diversity of these single-celled pathogens and the wide range of human organ systems they can affect. Take amoebaiasis, for example. Caused by Entamoeba histolytica, it's not just about debilitating intestinal illness or dysentery from contaminated food or water.
Which is bad enough.
Right. But in some cases, this resilient parasite can invade other organs like the liver, forming dangerous, life-threatening abscesses, highlighting its invasive potential beyond the gut.
Liver abscesses sound grim.
They can be. Then there's leishmaniasis, a complex group of diseases caused by Leishmania parasites transmitted by the bite of infected sandflies. This isn't a single disease. It manifests differently depending on the parasite species and host factors.
A spectrum of disease from one parasite group.
Exactly, ranging from disfiguring skin sores, cutaneous leishmaniasis, which can leave permanent scars, to severe, often fatal damage to internal organs like the spleen and liver, visceral leishmaniasis, which is a major public health challenge in many tropical and subtropical regions. Trypanosomiasis encompasses two major diseases. African sleeping sickness, spread by the tsetse fly.
We mentioned that earlier.
Yes. If untreated, it progresses from fever and headaches to neurological damage, coma, and eventually death. And then there's Chagas disease, particularly prevalent in Latin America, transmitted by the kissing bug, which can silently cause chronic, life-threatening heart and digestive problems years or even decades after the initial infection.
Years later. A silent epidemic, as you said.
It really is. We also have trichomoniasis, caused by Trichomonas vaginalis, a very common sexually transmitted infection that, while often asymptomatic, can cause unpleasant symptoms, increase the risk of other STIs, and lead to pregnancy complications. Giardiasis, often called beaver fever, is a common cause of waterborne dialyses from contaminated water, leading to prolonged severe gastrointestinal upset, malabsorption, and significant weight loss.
That was miserable.
It is. Finally, toxoplasmosis, caused by Toxoplasma gondii, is often acquired through undercooked meat or contact with cat feces.
Ah, the cat connection.
Right. While it might cause mild flu-like symptoms in healthy individuals, it can be devastating in immunocompromised patients, leading to brain lesions and encephalitis or during pregnancy, causing severe birth defects in the fetus. This broad spectrum truly underscores how protozoa are not a monolithic threat. They are a highly diverse group of pathogens, each with its own unique life cycle, preferred host sites, and clinical manifestations, necessitating highly specific diagnostic and therapeutic approaches.
It's clear that while they're all protozoal, their manifestations, preferred targets within the body, and global impacts are incredibly varied. So how does the medical arsenal respond to this diversity? Are there specific agents tailored for each of these varied threats?
Absolutely. The approach is highly tailored, reflecting the distinct biology of each parasite. We have several other antiprotozoal agents that are specifically designed to target these diverse infections. Let's start with atovaquone, known as Mepron. This drug is primarily used for the prevention and treatment of pneumocystis jirovecii.
Okay, pneumocystis.
Now, while pneumocystis jirovecii pneumonia was historically classified as a protozoal infection, it's now understood to be a fungus.
Oh, interesting reclassification.
Yes, but atovaquone remains a critical agent in that context, especially for immunocompromised individuals like those with HIV, where this pneumonia can be life-threatening, so it's often discussed alongside antiprotozoals.
Okay, understood. What's next?
Then there's metronidazole, widely recognized by its brand name Flagyl. This is a true workhorse drug.
A workhorse, so used a lot.
It's used a lot. It's crucial for the treatment of amoebiasis, trichomoniasis, and giardiasis, making it a versatile weapon against some of the most common protozoal infections. Now, there's a critical warning associated with metronidazole that cannot be overstated, and it's highlighted in all caps in our source for a reason. Do not mix with ETO.
ETO H alcohol. So no drinking on metronidazole.
Absolutely not. This refers to alcohol. The interaction with alcohol can cause a severe disulfiram-like reaction.
What does that feel like?
Extremely unpleasant symptoms like intense flushing, severe nausea, projectile vomiting, headache, abdominal cramps, and a rapid heart rate. It's a key nugget for listeners because it's a common prescription, and this interaction is often overlooked but can be quite distressing and even dangerous.
Okay, duly noted. Very important warning. What other drugs?
Next, we have pentamidine, sold as Pentum or Nebupent. This powerful drug is also used for the treatment of pneumocystis jirovecii pneumonia, particularly in patients who can't tolerate other drugs. But importantly, it also has indications for severe forms of trypanosomiasis, like African sleeping sickness and leishmaniasis, making it a broader spectrum agent for some of these more complex and severe protozoal diseases, often used in hospital settings.
So for the tougher cases.
Often, yes. Tinidazole, or Tindamax, is another important one, with a similar spectrum of activity to metronidazole, used for the treatment of trichomoniasis, giardiasis, and amoebiasis.
Similar to metronidazole.
Yes, often as an alternative or for convenient single-dose regimens, which can improve patient adherence. Less frequent dosing can make a difference.
Makes sense.
And finally, a very specific agent, benznidazole, which is now available generically. This one is explicitly indicated for the treatment of pediatric patients with Chagas disease caused by Trypanosoma cruzi.
Pediatric patients specifically.
Yes. Highlighting its specificity for pediatric patients and for Chagas disease caused by Trypanosoma cruzi really underscores the targeted, often age-specific approach needed for some of these more niche but still devastating protozoal infections. Here's where it gets really interesting. The tailored approach, where certain drugs are highly effective against specific protozoa because they exploit unique biochemical pathways that are essential for that particular parasite's survival, but are absent or different in human cells.
Like finding a specific vulnerability.
Exactly. It's like finding the perfect, unique key for each distinct lock.
That distinction between the drugs and their specific targets down to their unique biochemical vulnerabilities is absolutely fascinating. It's clearly not a one-size-fits-all scenario.
Not at all. Highly specific.
So looking across these other antiprotozoal drugs, even with their specific applications and distinct mechanisms, are there any general principles that unite them in terms of how they work, their safety profiles, or how they interact with other medications?
Yes, despite their individualized applications, there are certainly overarching general principles that apply to this broad class of other antiprotozoal drugs.
Yeah.
In terms of their indications, they are broadly used for the treatment of infections caused by susceptible protozoa, meaning that while specific, they are designed to be effective against the particular organisms they are licensed to fight.
Okay. Targeted but effective.
Their core actions generally involve inhibiting DNA synthesis in susceptible Antiprotozoa.
Stopping them from reproducing.
Essentially, yes. This is a common and effective strategy against many rapidly dividing pathogens, as disrupting the parasite's ability to replicate its genetic material effectively halts its growth, proliferation, and ultimately its survival within the host. It starves the parasite of its ability to multiply. Similar to the antimalarials, their pharmacokinetics varies by drug, again emphasizing that each compound has its own unique journey through the body, how quickly it's absorbed, how it's distributed to different tissues, how it's metabolized, often by the liver, and how it's ultimately eliminated, usually by the kidneys.
Again, critical for dosing and safety.
Absolutely. This isn't just academic. It profoundly impacts everything from how frequently a drug needs to be administered to its potential for accumulation and side effects in patients with kidney or liver dysfunction. When it comes to contraindications and cautions, there are general warnings that align with what we discussed for antimalarials. A known allergy or hypersensitivity to the drug is paramount,
That obviously number one.
as is caution in pregnancy due to potential fetal harm requiring careful benefit-risk assessment. Pre-existing conditions like central nervous system, CNS disease, significant hepatic disease, or renal dysfunction are also major concerns, as these can affect drug metabolism, excretion, and overall patient tolerance, increasing the risk of adverse effects.
So similar big picture cautions.
Generally, yes. Adverse effects for these drugs can generally include CNS effects like dizziness, headache, or confusion, which can impact daily activities and patient safety. Common GI effects, such as nausea, vomiting, or abdominal pain, are frequently observed, sometimes severe enough to impact adherence. Superinfection, meaning a new infection developing during the course of treatment, is also a possibility.
Like a secondary infection.
Exactly. Often due to the drug disrupting the body's normal microbial flora, allowing opportunistic pathogens to flourish. And for drug interactions, some broad categories to watch for include crucial interactions with alcohol.
That metronidazole warning again.
Reinforcing that critical warning where combining them can lead to a very severe disulfiram-like reaction. Interactions with warfarin, a common anticoagulant, blood thinner, are also significant, as some antiprotozoals can increase warfarin's effect, leading to a dangerous rise in bleeding risk.
Need to monitor blood thinning carefully.
Very carefully. Disulfiram itself, a drug used to treat alcohol dependence, also has significant and dangerous interactions due to the disulfiram-like reaction we mentioned earlier. If we connect all of this to the bigger picture, it underscores the common complex challenges in drug development, clinical application, and patient administration, regardless of the specific protozoa being targeted.
The consistent balancing act.
Exactly. There's a consistent, delicate balance that must be struck between achieving therapeutic efficacy, killing the parasite, and ensuring patient safety. It demands meticulous consideration of patient comorbidities, their other medications, and an acute awareness of potential drug interactions to ensure the best possible and safest outcomes. The entire process requires a deep level of clinical vigilance and patient-specific care.
So what does this all mean? We've covered a remarkable amount of ground today, from the terrifying swift reach of Plasmodium falciparum and the insidious long-term challenge of insecticide resistance with Plasmodium ovale that threatens global control efforts,
Huge challenges.
to the incredible tailored precision of drugs like benzonidazole specifically for Chagas disease in children, and the critical, often life-saving warnings around common medications like metronidazole and its interaction with alcohol.
That alcohol warning is one everyone should remember.
Definitely. This deep dive has truly shown us the constant microscopic battles being fought on multiple fronts to protect global health. Battles that unfold in our environments, our communities, and within our very bodies.
Indeed. We've seen how understanding transmission routes, whether it's through an insect's bite or via ingestion and direct contact, is absolutely fundamental to prevention. We've explored the unique biological characteristics of each parasite, like the varying severity of different Plasmodium species and the clever dormancy of P. vivax.
The hypnozoites.
Those hypnozoites. And we delved into the intricate actions of antiprotozoal agents that strategically target different stages of the parasite's complex life cycle. Crucially, we've also unpacked the extensive yet vital list of precautions, contraindications, adverse effects, and drug interactions associated with these powerful medications.
It really drives home the complexity.
It genuinely encourages critical thinking about the delicate and ongoing balance between efficacy and safety in medicine, and how it's never just about finding a drug that works, but one that works effectively and safely for that specific patient in their unique circumstances.
As we wrap up this deep dive, consider this. With the challenges of drug resistance emerging in some areas, like the mosquito resistance to insecticides we discussed for Plasmodium ovale, and the adaptable nature of these single-celled organisms,
They are very adaptable.
what future innovations in prevention and treatment, perhaps entirely new drug classes, advanced vector control methods, or even vaccines, do you think will be most crucial in the ongoing multi-generational fight against these tenacious protozoal infections?
That's the big question, isn't it? This raises an important point about the long-term sustainability of our current strategies and the continuous urgent need for cutting-edge research and development to stay not just abreast, but ahead of these adaptable microscopic threats. The journey to being truly well-informed about global health challenges and the solutions required to face them never truly ends.